So let's do this problem. Here's what we're given. Well, let me just show you it in the book. So you know, if you're watching this, you can. Let me zoom in. So this is the problem we're kind of looking at. We've got a capacitor that's hooked up to a battery. And the battery, the capacitor has a capacitance. We get a certain amount of charge, depending on what this is. Then we disconnect the battery. So all that charge, all that energy, all that stuff is still in there, right? But I've taken the battery away, and then I put in a dielectric material. That's going to change the capacitance, and therefore it's going to, well, we're going to change. We want to know. So what we want to know is this: after I disconnect the capacitor and stick this dielectric in there, well, I want to compare how much energy was stored before the dielectric and how much energy is after, and then we want to talk about why. We'll probably run out of time, but. Okay, so let's well, what do we know? We know U is equal to well, let's start off with 1/2 Q naught squared over C naught. Okay, and so that's how much, and oh, this is U naught. Okay, so that's that was pretty easy. That's my answer. But now let's put this stuff in here. Now I'm going to disconnect it from the battery. Then I'm going to place this in here. Now what can't change? Remember, I've got a certain amount of positive charge on this plate, and negative charge equal over here. These things are not going to go away, these charges. So I'm going to stick this in there. So I'm still going to have, I'm still going to have the same amount of charge. It's still going to be Q naught squared. But now, I'm going to have a new capacitance, and that's going to be kappa times C naught. Okay, but look at this. Look at this. 1/2 Q naught squared over C naught. Well, that's just U naught. So this is going to be U naught divided by kappa. Now, okay, that's my answer, but what does it mean? Okay, double rainbow guy wants to know, what does it mean? And by the way, I'm a big fan of double rainbow. I think he's a cool guy. All right. Now, anybody who cries because of a double rainbow, he's all right. Now, let's take a look at all the kappas we got. What do you notice about all the dielectric constants? Okay, I hope you can see this. They're all greater than what? 1. Which means, and I'm dividing by it. So what does that mean happens to the energy stored in my capacitor? It dropped. Where did the energy go? Energy can't just disappear. Okay. Well, it didn't create a spark. Those are all wonderfully good ideas, but no, what happened was this, and I think I have just enough time to explain it. Let me redraw the capacitor like this. All right. Now, okay, everybody watch it. Look. You can see that this is going to be a lot less energy. I mean, if I put strontium titanate in there, I've lost, all but about 0.5% of my energy went away. Where did it go? Okay, so here's my slab. I got to place it in there, right? So here's my slab of dielectric. Well, I got positive charge right here, negative charge right here. What does that do? Well, that creates a bound charge. And I get a little bit of negative charge up here and a little bit of positive charge right here. And what does that do? That attracts the slab. So this is actually going to feel a force. And that force is going to be displaced as I move it through here. So we're doing work. In other words, the capacitor does work on the dielectric as you move that dielectric in. Now, if there was no friction or anything, the dielectric would be drawn in and it would swing back and forth like this. Okay, but obviously there is, or somebody is holding it back. In other words, the act of placing the dielectric in there, either through friction or from some outside force that's like backing it up, takes away energy from the capacitor. So if you disconnect the capacitor so that it's not connected to the battery anymore, and then you place that dielectric inside there, work will be done on the dielectric, and it will be dissipated into the environment, either as heating or friction, or as somebody who's doing work against that attractive force there, and so you lose energy. So the energy. So really, when you think about, okay, what was our loss in energy? Okay, which is mu minus mu naught is going to be negative. That's going to be mu naught times 1 over kappa minus 1. And this is going to be a negative value. So this represents how much energy I'm going to lose when I place the dielectric in there. This is going to be a negative value, right? Because kappa is greater than 1, so 1 divided by kappa is a number a lot less than 1. Minus 1 gives me a negative value. This is my lost energy. Lost by the capacitor, not by the universe, okay? That is all.